Actually, I'll make that. All right, here we go. Time to lock in. Let's finish this out. Let's finish this PowerPoint. Correct answer is B. Okay. It's going to be brighter. You can't get something for nothing. There's going to be more magnetic force opposing your motion. Okay. Tell your neighbor. Correct answer is B. Beautiful butterflies. You have more loops. You have more N, like your N is higher. Good? This one is not as straightforward as you would think. I'll give you a hint. Consider Ohm's law. Oh, it's only on your parking lot. It's only on your parking spot. Have a conversation.
Chairs.
Correct answer is. Correct answer is C. Okay. So, yes, there's more voltage, but because the length is twice, the resistance is resistivity times the length over the area. You have twice the length, twice the voltage, but twice the length. Good? Everybody good with true? Okay, has that. It's creating its own little electromagnet that's in opposition to that. Yeah. Okay. So I'm assuming Dr. Carlson showed you the one where you drop the magnet down the pipe. Okay. That's this. It is cool. All right. So you get these eddy currents, these whirlpools. If you pull conductor through the magnetic field. So this is that magnetic friction. It's a form of magnetic braking. Okay. So you can, if you have a wheel that's made out of conductive, like you've got some kind of like a brake pad behind your, not the pad, just a disc behind your wheel, and you have magnetic field, you can cause that to have braking. If you have magnetic field, causes it to slow down. Okay. Good with that. This is how metal detectors work. If you are going through here, you got a coil of wire with current going through it, creating its own magnetic field. And if you pass through here with metal, that's going to induce a current, and it's going to induce a current over here as well, because it's changing magnetic field. And that's when it picks up, oh, I got a piece of metal. So that's why you need to walk. You have to be moving. Or if you've ever been in the airport and they say, put your hands up, and you get the moving, you have to have a moving or changing magnetic field. Does that make sense? Okay. Last question. That's kind of a, I don't know where to throw that one, so here it is at the end. Have a conversation. Recognize these are centimeters. I should make these easier. This seems silly to go through all these decimal place movies. Okay, does everybody go with slope times the area? Okay, I think it's E. If you made those centimeters. Everybody go with that? Slope times the area? Okay. All right. So that was review of last year. All right. Here's some new stuff for you. So, if we have a magnetic field that's increasing, flux is going in, change of flux is going in, induced magnetic field, we have current going through this thing, counterclockwise. Good? At a more fundamental level, the thing that causes current is an electric field in the wire. You okay with that? So there is also an electric field going in this direction, counterclockwise. So here's the step. Ready? If we take out that ring, that conductive ring, there's no more current, but there's still an electric field that's created or induced. So a changing magnetic field induces an electric field. So an electric field can be created by traditional, what everybody's used to, charged particles. A Coulomb electric field. And this is a non-Coulomb electric field created by a changing magnetic field. Crazy, yeah? And obeys the same alternative right-hand rule. Good with that? Okay. So, here, Jared.
Can you go back 1 second?
Yep.
So with those arrows, those wouldn't be to scale, right? Because they would all be the same magnitude.
Ooh, good question. Hang on to that thought. Coming soon. Okay, so here's our playground. We've got a solenoid, current flowing through it, creating a magnetic field going up. Okay. We're going to increase the current. So the flux in the middle here is increasing. So we have flux going up, the change in flux going up. Okay. So the magnetic field that's going to be induced is in opposition to that, creating an electric field going that way. Good with that? Okay. And so, oh, okay. This is looking, shoot. This is looking from the bottom of this. Wrong way. This diagram is looking from the bottom. So we have flux going in. It's increasing, so we're opposition to that. It's going this way. Okay. So this induced EMF. Okay. So voltage is equal to current times electric field times distance. Very algebraic, constant last year stuff. Okay. We can have a line integral, electric field times distance. It's an enclosed loop, so it's a circle. So it's kind of looking like Ampere's law. Yes. But now it's with electric field. Okay. Usually this is going to be a circle. So this is going to be like 2 pi r. Okay. So this is actually a more complete expression of Faraday's law. Okay. And on the equation sheet, should copy and paste this. It has just this. That's what it has on the AP equation sheet. Good with that? Okay. So here, let's you. So this is going to be the left side of the equation. Here's our circumference. And we're assuming that the electric field at a certain distance away is constant, so we pulled that out. So that's that. Okay. And then on the right side of the equation, we've got a certain area. Okay. So your area is this. And we're seeing, how quickly are we changing this magnetic field.
Shouldn't a closed line integral electric field always be 0? Because it's the gradient of the voltage still.
Right. So we're inducing the EMF.
Yeah. But if it's the gradient of a function, then it should be a conservative vector field. And a closed line integral should give you 0.
But it's like I'm not saying we're creating energy, but it's like we're like, so how would you argue that if I have a conductor here, where that current came from? You're arguing from a math point of view.
Yeah,
I'm arguing from a physics.
I'd like to know why. Does Gauss's, because if it is conservative, does Gauss's law still work in this context when you have the
from a charge point of view, or like Gauss's law in a general sense, or in a
if
like
you have a non-Coulomb electric field and you take the divergence in a closed surface, is that still going to give you the charge enclosed? No.
before I give a definitive stance, let me think about that.
Okay.
My gut says no, but I'm not.
That's what I was thinking.
I'm not gonna bet the.
Not necessarily electric field,
Yeah.
but is it? Yeah.
Let me digest that a little bit. Okay, so I was seeing how this works, the area, okay, and then you have 2 pi r on the left side. So pi's cancel out, one of the r's cancels out, and you're left with this. The electric field is equal to r over 2 times the rate change of magnetic field. So Jared, to answer your question, it was drawn to scale. Cool with that? So this is inside a solenoid. So you can't just say it goes on forever. Okay. So um, this is just a summary of what we just did. So here's our playground. We're inducing an electric field. It's in the opposition to change it in flux. And that electric field is going. I should really switch these around. Oh, wait a minute. Now are we going the right way now? Now we are going the right way. What is going on? I didn't take that diagram over there. James.
Are the equations that are the solenoid, or is that are like from the center of the solenoid?
The R is from the center of the solenoid. Mm-hmm. Yep. So here's, yeah, solenoid's like out here or something.
So
Tell me.
there's no induced electric field in the solenoid? Is that why we measure it? What about the massive field?
Yep. Yeah. Don't see anything weird there. All right. So moving on. Um, so Clark Maxwell was like, well, if we know that a changing magnetic field induces an electric field, what about the opposite be true? It's just like a hunch. So we tested it and found out that was true. So a changing electric field creates or induces a magnetic field, and it also obeys the right-hand rule. That diagram does not do a good job. So assuming this is, yeah, that's a wrong diagram. Sorry, I didn't make it. Just pulled it out of a book. Yeah. Okay. And so, Clay.
Actually, on the slide before this, what happens if it's like not a circle? Or like, is this still the same thing? It like doesn't matter.
What is it? Doesn't matter.
Like solenoid or like the shape of the changing magnetic field. Like if it was like a square or like a really long rectangle.
Oh, I see what you're saying. Yes, that'll mess with that.
But we're not gonna do that though.
Okay, so this is where how electromagnetic waves work. So a changing magnetic field that's sinusoidal, is always changing, induces a changing magnetic field that's always changing, which induces a changing electric field. It's always changing, and this is how it self-perpetuates through space, no medium required. Crazy. Okay, turns out that the speed of light is equal to, and this is after a lot of experimentations, 1 over, this is not something you need to know, this is just like, oh, that's, appreciate the, okay, 1 over the square root of the permeability of free space times the permittivity of free space. Free space meaning a vacuum. Okay. So you can get different this for different insulators, right? Like the what's dielectric stuff. And you get different stuff. Like you stick a piece of iron in an electromagnetic magnet, you get a different coefficient for that. Okay. But this is talking about a vacuum. Everybody goes B. Okay. It's going this way. Decreasing, going that way, in opposition to that. Okay. Still right hand rule. Tell your neighbor. Correct answer is, everybody go to A. Increasing. Okay. So counterclockwise, tangent to that, the left. B. Okay with up. Still counterclockwise. C. E. Good with that? Okay. So this is in a solenoid. We're going to have a constant rate of change of the magnetic field. We're going to look at this. So here's the solenoid. We're going to look at this. We're going to try to evaluate the strength of the electric field that's induced at this location. Thumbs up when you have a guess. You're just evaluating this. B is the answer. You want to do the lowercase r. It's the perimeter, circumference. Okay. because that's where we have our Amperian loop. Thumbs up when you have an answer. Have a conversation.
Using the smaller units.
Using discharge from the wall, we know the area is constant, so we can test that. The area is higher B or C. Change in B is just C change in C.
Correct answer is D. Because, okay, so everybody good with, so we're area times dB/dt. That's just, this is just C. And then the area is just this part that we care about. Good with that? The portion that has the magnetic field. Okay? So, putting these together, tell your neighbor. There we go to C. This is the same conclusion we came to right here. Good with that? But what happens if we are now outside the solenoid?
Is it that pretty constant outside of the circle?
Ideally, the magnetic field is zero outside of a solenoid. Okay. Correct answer is sorry, I was doing perimeter. Or I was doing circumference. I was doing the left side of the equation. Correct answer. Does everybody have? I got an answer. Okay. Everybody have an answer? Okay. Correct answer is E. Okay. The reason why we stop here for change in flux is because this is the only area that has magnetic field. I don't care about this part. There's no magnetic field here. I care about the change in flux. Good with that? Correct answer for this one is B, lowercase r. Because what I'm trying to do is evaluate what's the strength of the electric field here. Okay? The magnetic field of a solenoid has some value here, but outside theoretically is 0. But we're looking for the electric field, not the magnetic field. Okay? How are we doing? Does that make sense? When to use capital and lowercase? And why we're doing that? Tell your neighbor. Everybody goes B. Okay? So outside the solenoid, it drops off as 1 over R, which we would expect to get weaker as you go away from the solenoid. Good with that? Watch yourself. It's an electron. Tell your neighbor.
Is that electron?
Just stationary electron.
Okay.
Okay. Correct answer is D, dangerous dinosaurs. Okay. Flux is going in, increasing. So we're in opposition to that. Electric field goes this way. Electrons being forced in the opposite direction of the electric field. Okay. So, a classic playground free response problem, something like this, where you have a solenoid, and then you have galvanometer around connected to this wire here. Okay. Okay. So here you have a generator. It's spinning. This loop of wire, causing not a change in the magnetic field, but a change in the area to generate flux, a change in flux. Okay, and so that the area change is governed by this. So in this arrangement, we met like there. That would be maximum flux. This would be minimum flux. So we're looking at the rate of change. So we take the derivative of that, and we get that for so this is like how quickly it's spinning. Okay. So it's a function of how fast it spins, the area, magnetic field, and how many loops of wire there are in the sinusoidal. Okay. So here we have maximum flux, but we actually have minimum rate of change of flux. Here is zero flux, but the greatest rate change of flux as it goes. You all right with that? And follows the cosine versus sine function. Like they're off by 90 degrees or pi over 2. Okay. Have a conversation. Let me just give you a hint right now. We're not inducing anything. We're just creating, like it's just a magnetic field. It's just a loop of wire. We're gonna tell a story here. This is step 1 of the story. Up is the positive direction. Correct answer is 2. Yes, no, maybe so. You're just doing this. It's just that's the strength of it. You're just creating a magnetic field. And it's going current's going this way. Everybody okay with that? That's why I'm getting down. No, 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 no.
Up is the positive direction of the field, and so if it's aimed downward, it's
Oh, wait a minute. Why don't I like any of these options? Sorry, B's the best. Sorry, not B. One's the best option. As the current goes down, the magnetic field's going to go down. I think a better, like, here's what I was. That's what I was thinking it was. Up is the positive direction. It's creating a magnetic field going down. Yes? The current's positive. It's decreasing. Current's decreasing. I mean, tell me if I'm wrong. I mean, I'm okay being told I'm wrong.
I really wish it was down as defined as positive direction, so he doesn't have to do another reverse thing.
Let's just say, let's say up or down. Or I could just switch to these two. Switch direction of current. Okay. Let's we're gonna run out of time for this story.